Hello everyone, I hope you all are doing good. Till now we have been discussing about nucleation for liquid to solid state transformation as well as for solid to liquid state transformation. Today we will be discussing about growth. Uh, we have seen the nucleation rate versus time plot and started the discussion on TTT diagram. So today we will be discussing about growth. So as we know that solidification is nucleation and growth. It's a two-step process. So once a nucleus is formed, nucleus is like it has got the size greater than the critical size. So it will grow in order to reduce the free energy. Now this growth or the growth rate will be limited by many factors like the kinetics of atom attachment to the interface. This interface between this is a solid phase and there you have liquid phase. So this interface between solid and liquid, there are around the solid you have large number of atoms in the liquid. So in the liquid, so it will the growth rate will depend on this, the kinetics of the atom attachment to the interface and also the capillarity which is indirectly which is related to say interface energy and the say gamma SL we say and the curvature of the interface and the curvature of the interface. So capillarity will also influence the growth rate, and the third one would be the diffusion of heat and mass means these are the diffusion of solid atoms. You can say if you have an alloy solidifying, then the diffusion of solid atom will also influence the growth rate, as well as these three factors. Especially this diffusion plays a very important role. But you will see most of the growth rate, the equations are mostly derived in a simple way by by studying the kinetics of atom transfer or atom attachment and detachment at the interface. So these are the factors you have to remember. Now when this when the nucleus grow, or the interface, the grows, then what happen? The growth can have different types of morphology, and depending on the morphology, of the interface, the growth is classified into two types. One is faceted and another one is non-faceted growth. So faceted growth and non-faceted growth. So these are two different types of growths. The surface plays an important role. So when I say faceted growth means you can say the surface would look like a typical representation you will see in most of the. This is actually 3D. This is one type of morphology, and another one is you have a crystal which is growing, but so this is like here it is called faceted, and here it is non-faceted. Non-faceted means the growth is isotropic in nature, means it can grow in all the directions almost equally, but here faceted means the growth is preferential. Like you see, these are the particular planes on which the growth is. In this direction the growth is more than this direction, so you end up getting different planes exposed to the surface. So you end up getting a surface like this, where you see the crystallographic directions are still visible in the macro scale also. So faceted means the direction you have got preferential direction for the growth. Here in non-faceted means you don't have any preferential direction, the growth is uniform in all the directions. For non-faceted, as I said, the growth is isotropic. Isotropic means it is almost equal in all directions, but some anisotropy may exist because of the interface energy. You see, if it can grow in all the direction, without having any preference to any particular direction, then during the growth the surface can become curved. So if there is a curvature, depending on the curvature, surface energy will vary. We have discussed this thing in the class. So this will lead to some anisotropy, and because of this, actually this tree like structure, or if you see in real materials, we get dendritic structures. So which is because of the anisotropy caused by interface energy, which is caused by surface curvature, or also this interface energy is driven by the solute precipitates, or removal of solid from the solid part, which is that we'll discuss later. So let us write down some properties of faceted and non-faceted crystals. So first we can say the non-faceted one actually interface. Actually, the interface will be macroscopically. Interface is macroscopically smooth, but atomically rough. Atomically rough means the surface. If you see the atomic structure, the surface should be very rough because there is no preferential direction for the growth. So atom can go and get attached to the surface at any point. So that's why the surface will be atomically rough, but because of that again overall, if you see in the macro scale, the surface will be smooth. And other properties, the growth is isotropic. And this is mostly found in metallic materials because the metallic bond is non-directional. So this is what we are writing here for non-faceted. So as we know that metallic bond has got no preferential direction for making the bond, but if you see non-metallic, say different covalent bonds, they have got some preferential orientation. So the bonding is directional, it is not non-directional. So when you have say the material with complex crystal structure and directional property, in that case we can expect such faceted crystals. The growth will not be isotropic, it will be anisotropic. So most of the metallic material generally exhibits this kind of non-faceted structure, but local anisotropy due to surface or the diffusion of solute at the interface leads to this local anisotropy, which gives the dendritic formation. So in summary, we can say non-faceted interface are those which on macro scale are smooth, but on atomic scale the interface will be rough. If you see the faceted, atomically they are growing on along different planes. Now when they become bulkier, then the surface, in bulk also this plane will be there. So then in bulk scale they look very rough. So on atomically they are smooth, but on bulk they are rough. So these are the different ways of growth of interface, and then whether the substance will be faceted or not, it depends on many factors. It is not that you always get non-faceted for a type of material. It can, a particular material can give you different types of interface depending on the processing route. Say for example, if you get a faceted interface from vapor deposition method, you can get a non-faceted interface if you go for liquid to solid transformation. So there are different ways and the diffusion of heat and solid plays an important role here. These things you should remember. So now the growth rate when you have a nucleus. then it will grow for completing the solidification. If we see the kinetics of atom transfer around the interface, then we can simply say that the growth rate will depend on, you see, both the solid and liquid is at relatively high temperature or maybe very close to melting point. So they have got thermal energy is maybe sufficient enough for diffusion. So if there is no diffusion, if atom cannot transfer to the interface, then there will be no growth. But because of high temperature, there will be vibration in the atoms. Now some atoms will go and attach to the solid nucleus, and some of them will again come back. So the growth rate will depend on the net difference between the attachment of atom and detachment of atoms to the interface. So the growth rate of the nucleus during solidification will depend on the net difference between the attachment and detachment of atoms from liquid to the interface. So it will depend on the rate at which the attachment is actually taking place. So the rate of attachment, that means the rate at which atoms comes and get attached to the solid, the rate of attachment will depend on the rate of diffusion of atom in the liquid. And it will be related to the activation energy of diffusion. It will depend on the activation energy of diffusion or the rate of diffusion of atom in the liquid. So the rate of attachment and the rate of detachment of atom. The detachment rate it will depend on the number of nearest atoms. So the solid, when the solid is formed, say you have a solid surface being formed. Now the surface is part of a crystal structure, say be it BCC or FCC or whatever. So although macroscopically it may look flat, but microscopically, atomically, if you see, maybe the surface is something like this. Who knows? So there, what happens then when the atom goes there on the surface of the interface and sits there, if the atom is sitting here, say here one atom is coming and sitting, so it will be exposed to different number of atoms. If it is sitting on the surface, it will be exposed to different number of atoms. Say if this is the crystal structure. So depending on the number of the nearest atoms that is available for this atom coming to the surface, the detachment will be limited by those number of nearest atoms. So this is called the number of nearest atoms, number of nearest atoms, or you can say neighboring set, number of nearest neighbors. Binding the atoms to the interface. So when a liquid is coming from, say, liquid to the solid, say let us consider this is the crystal structure. This is just for demonstration. So if an atom comes here, if it goes there, so if it is facing 1, 2, 3, on 2D atoms, so this can make a bonding with this and bonding with this. So if it goes on the surface, it will have only, if it goes here and make the bonding, it will have only one neighboring atom for the this solidification or the growth. So this will not be favored, but this will be favored. So this has the higher probability of staying there than this one. This one will detach very easily. So this detachment, actually the rate of detachment depend on the number of nearest neighbors binding the atoms to the interface. So if there is one atom, if the atom is here, then you see in the liquid it has more number of neighbors binding the atom. So it will try to go back there. So the push or the pull back is stronger than the pull in the solid directions. So that's why it will have higher probability of getting detached than this one. So what we can say that from this, so it depends on the detachment rate, depends on the number of nearest neighbor binding the atoms to the interface, and this depends on the surface roughness. What the surface means? Interface roughness. Write it, interface. So it will depend on the interface roughness. If it is rough, then it will expose more number of atoms for making the bonds. This is nothing but it increases the surface roughness, increases the number of unsaturated bond, the number of unsaturated bond increases. So with roughness, you see, so many things happen. Now you can imagine that when you have a faceted growth, the surface is flat. So the attachment of atom to the surface will be very difficult compared to the, say, the non-faceted one, where the surface is atomically very rough. Then if it is very easy for rough surface, if it is very easy for atoms to get attached to the rough surface, you will have to provide less undercooling for solidification or for faster growth. If it is flat, then you will have a very less probability for the atom to stay there, or it will be very difficult for making the crystal glow or for making the atom get attached. Then you have to go for higher undercooling. So you have to go for higher undercooling. The temperature of transformation has to be very low. So that is how faceted and non-faceted growth. The understanding of these things is very important. Now as I said, if say the surface is rough, so in 2 dimension we are representing these things. So this is say one crystal structure. This is the interface. So above you have liquid, below you have, this is solid. So this is part of the solid and this is the interface. So here the interface is rough. So as we just have discussed, or we have said, as we have just said that the growth of a crystal is determined by the probability that the atom will, suppose if one atom is coming here, say here in this location, so it will complete this structure. So we are considering a simple cubic structure. We are considering a simple cubic structure. So the growth is determined by the probability that the atom will remain there and become part of the crystal. And then this probability increases with increase in number of nearest neighbors. Like here on 2D it looks like you have 2, but if it goes here you will have 1. So if it goes here you will have 1, 2, 3. So in 3D it will be even more. You will have 1 on this side front, one you will have 1 on the back. So you have 5 here. So the coordination number here is 5. Whereas you see the coordination number here is only 1. So if the coordination number is more, that means it has the higher probabilities to stay there. So this increases the probability. So the growth in this case will be, for rough surfaces, will be faster, growth rate will be faster. So if nearest atom increases, the driving force required for solidification will be less. So if it is less, units require less undercooling. So you need less undercooling for solidification. So if this is atomically, the surface is not flat. So these are the few points you have to remember. But if the surface is atomically flat, then what we have just discussed, then for flat surface, if the surface is atomically flat, fewer neighboring atoms will be there. So it will, if you have, it will reduce the probability. Probability that the atom will stay there. In that case, you will have to apply. You have to apply a higher driving force. So for higher driving force, you have to go for higher undercooling. Let us consider this part to be. So what will happen? Suppose this is the crystal structure, the flat. So what will happen? Suppose one atom comes here and make a burning. Of course this is continuous in this direction also. Then another atom will come here, another atom will come here, another atom will come here. Now the next atom will not go here because here the probability will be less. You have one neighbor. But if an atom comes here, it will have two atoms, neighboring atoms. So here the probability will be higher than this location, this position. So in flat surfaces, in the case of faceted growth, the direction of growth remains very uniform throughout the completion of throughout the solidification. So that is how you get this faceted crystal growth, and that is, in that case, you get non-faceted crystal growth. And as it is not directional, it is random. One atom can come here also. As the surface is rough, randomly it will happen. Wherever you have some roughness, it will happen everywhere. So the surface will continue to grow. But in this case, it will lead to planar growth. Here you will have non-directional growth. So in general, what we can say, in general we can write if the difference the structure and the difference between the structure and bonding properties increases. If the difference between the structure and bonding properties of solid and liquid, these two phases, if it increases, then you will have a very sharp transition. Then you will have very sharp transition, which causes the reduction of the interface region. Interface, the region is very narrow, and faceted growth is generally found when you have very sharp variation between the liquid properties and the solid properties. So very sharp change in the properties makes this region very thinner and it becomes flat, reduces the interface region thickness, and it leads to flat interface. And if it gives a flat interface, then the growth is anisotropic, and also you need higher undercooling is required. So you see, if the bonding and the structure of solid and liquid phase, or the two different phases are very different, then the region of the interface region will become very narrow, and this causes this interface to be very flat. If the interface is very flat, there will be the growth will be very difficult, and because of this you need high undercooling, and the growth will also be anisotropic. But in metals, if you see the metals, the structure and bonding generally in the solid and liquid phase is similar. So the transition from liquid to solid phase is very gradual. So the transition region is little bit wide between the solid and liquid interface, because it is very rough. So in that case the solidification becomes easier, and you get isotropic growth. That means growth is almost uniform in all the direction, but local anisotropy, because of solute and the interface energy, actually we get dendrites. That we will be discussing later, but these things you try to remember. Now the question is, then how will I know whether the metal will be the growth will be isotropic or anisotropic? There is something called melting entropy. Melting entropy. So this is a non-dimensional parameter alpha, which is delta S, say, of fusion by R. R, you all know what is R. R is universal constant. So this is called entropy of fusion. Delta S, entropy of fusion. As you know, delta G is delta H minus T delta S. So at fusion temperature, we can write like this, or melting temperature, or solidification temperature. At equilibrium, at T, Tf, delta G will be 0. So delta SF is delta HF by T. So this is actually this entropy of fusion. So if you know the heat of latent heat of solidification, you can find out the entropy of fusion. So if this value is less than 2 for the simple cubic structure in analysis, then you get non-faceted crystal. Non-faceted crystal growth. If it is greater than 2, you get a faceted crystal growth. So these things, this is just a non-dimensional entropy parameter. Is called melting entropy. This parameter tells you whether you will get a faceted growth or non-faceted. But again, I am saying you can, for the same material you can have faceted as well as non-faceted growth depending on the processing rule. And if you see the growth rate, for small undercooling, if your temperature is less than Tm but very close to Tm, it is less than Tm definitely but tends to Tm. For small undercooling, we can write growth rate that we will discuss, but at this moment you just remember this HKL delta T. So growth rate is a function of growth kinetic growth coefficient or kinetic rate coefficient. This is called kinetic rate coefficient, and this is undercooling. So this is undercooling. So this kinetic rate coefficient depends on the plane, crystallographic plane. So for crystalline material, different planes have got different values of this kinetic rate coefficient, and depending on that, growth in different directions will be different. As a result, you end up getting different shapes. Say one precipitate, if one precipitate is being formed in a solid, now the precipitate, if it is crystalline, say intermetallic compound being precipitated, then what will happen? The growth rate can be different in different directions. So the morphology, the shape will vary depending on this value of the coefficient. We will derive this relationship after this class, but just to give you some idea. You see, in the last lecture we had discussed the morphology of graphite. You have nodular, you have needle like shape, as well as you have flakes. So these are mainly because of different values of this growth coefficient for different crystallographic plane. So this you have to understand. Of course, everything is related. You cannot say one particular factor in an isolation from all other. You have to see everything together. Now you see Jackson in 1968, he did some analysis and found that for different values of alpha, say 1, 5 and 10, K100, K111, this is the coefficient of this plane for simple cubic crystal. So Jackson. he found that different values of k, 0.2, 0.007 and 0.1, 2, 3, 4, 5, then 5. Here 0.1, 1.4, 20.0. So when you divide k 1 by k 100, the coefficient you get 0.5, 0.4 and then 20. So this is 10. So what it tells you, this ratio is for higher values of alpha, this value is very high. That means the growth in 111 direction will be very high. So if you have a crystal, say this is 111 direction, so you can have a crystal like this, long crystal in this direction surrounded by 100 plane. It will grow preferentially in this direction, 11 direction, and it will be surrounded by 11 plane. 100 plane. So this is what you need to understand. If you see, if entropy of fusion, as we have written, alpha equal to delta SF by R. So if entropy of fusion increases, if it is very high, the attachment of atom will be very difficult. Entropy of fusion is very high means there is a sharp change from the liquid to solid phase. The moment you melt the solid, the randomness is very different, hugely different. That is why entropy of fusion is very high. So if it is so, that means the interface will be very flat. If the interface is very flat, then the attachment of atom will be very difficult. But then in that case, how will you grow your crystal? In such cases, the defects are of particular interest for industrial practice, like say defects like screw dislocations or twin boundaries. This becomes important. So as alpha increases, this means delta SF increases. That means there is a sharp variation in the properties. And when there is sharp variation in the properties, you will have faceted kind of crystal growth, planar crystal growth, and it is difficult. You have to go for higher undercooling. But you should have defects like say screw defects or twin boundaries. Other kinds of defect can be removed by the attachment of atoms and will not give any advantage for higher entropy of fusion if your process is involved with higher entropy of fusion. So this is all for this part. You remember these things. Now the question is, we will derive this growth rate equation.